This is part 5 in doing the duct design calculations. In this video we're going to discuss the concept of equivalent length. When we do our duct design calculations, we need to take into account the resistance to airflow created by different fittings. In your manual, you will find a series of pages that have grouping of different fittings and their associated equivalent length. Now, basically equivalent length means that if you were to take a piece of ductwork, let's say in the case of this elbow here, it has an equivalent length of 10 feet. What that translates to is if we take 10 feet of straight ductwork and you were to measure the pressure going in and the pressure coming out of that 10 feet of ductwork, that the pressure going in and coming out of this elbow would be equal to the same pressure drop over 10 feet. If you took this B fitting, which has an equivalent length of 35, you would be looking at 35 feet of straight ductwork. If you look at the A fitting, which has an equivalent length of 55 feet, you would have, in fact, the equivalent distance of 55 feet of straight ductwork would be equal to the pressure drop through this one fitting. So the type of fitting can really affect the how efficient air is moved through the duct system. And different kinds of fittings will have different effective lengths. In the case of these side elbows, the width will determine what the effective length is. So depending on the width of your fitting, you could look at this table and figure out what the effective length would be for the fitting. So these are what we call side elbows. Here we've got what we refer to as riser elbows. These are elbows that either can turn the ductwork from horizontal to vertical, either vertically up or in fact vertically down. And you can also have what's called a transition. In the case of the return air, where the air is flowing from the house back to the furnace, ductwork further away from the furnace could be smaller, and then you would put this transition in so that you can then add more air into the duct system. So these are some of your return trunk fittings. With the return air, we can use the actual joist spaces, that's the space between floor joists, or even stud spaces in walls, to act as return ducts. And so often we will use a stud space to bring the air down, and then that air gets into a joist space, which is then allows the air to carry through the joist and then ultimately get picked up by the duct and then brought back to the furnace for reconditioning. But these transitions, air flowing from the joist into the duct, are quite, they've got a lot of resistance to airflow. You notice that when air enters the duct at the end, it's relatively free-flowing, so the equivalent length is only 25. But any return air that enters the duct between the furnace and the end of the duct, well, this results in a much higher resistance to airflow, and you can see that the air turning in here ends up with an equivalent length of 60 feet. So these fittings and the number of intersections can be very important. There is a concept in return duct design called turbulence. I equate turbulence to essentially thinking about traffic on a highway. If you've got a 4-lane highway coming in, and you've got a 4-lane highway running this way, you've got now all of a sudden 8 lanes trying to merge into 4 lanes, and you know what kind of turbulence that creates with the traffic. And so we've got the same issue in terms of our return air. And so for return air number 1, as it flows through the duct, it bumps into R2, and in this case it also bumps into R3. That means that R1 has a turbulence at R2 and at R3. So it has a total of 80 feet of turbulence when it gets to this transition. R2 only bumps into R3, which means that it has only 40 feet of turbulence before the transition. And R3 would have 0 turbulence because it is next in line to meet the transition. Now you'll notice that after this transition, the turbulence effect starts over again. R4, as it enters the duct and travels towards the furnace, you'll notice bumps into R5. Now notice that R5 is actually a double return air, and notwithstanding that it's a double joist and a double stud, it's considered to be one single return, and so therefore you would only add 40. You would not add 80 in this case. And R5 being then the nearest to the furnace would have 0 turbulence added. Now we've got our actual inlet grills. You can have a grill on the floor or you can have a grill on the wall. And it doesn't matter whether the grill's in the floor or in the wall. The air traveling through the grill and turning, in the case of the stud, turning down, is equal to 10 feet. And similarly in a floor register, a floor grill, the air going through the grill and turning is also equal to 10 feet. Now when you've got air coming from the first floor into the basement, or even from the second floor making its way down into the basement, you've got a stud space, you've got a plate opening, so the air comes down the stud space, through the plate opening, and into the joist. In the case of a partition that is perpendicular to the floor joist, that turn, that air coming down through the plate and turning into the joist, is worth 15 feet. If you've got a partition which is parallel with the floor joist, that turn is a little bit more restrictive, and you can see it's worth 25 feet. Now, as a second floor return would come down, if it has to jog in the first floor ceiling over to a wall, then come down, get to the basement and turn again to get into the ductwork, we would have 3 turns. And so it's not uncommon that your second floor return would actually have 3 times this A fitting.